So in this video, I'd like to go over the solutions to the synthetic root practice worksheet. So again, uh, uh, you're started with a certain number of starting reagents and asked to be able to convert things from one chemical to the other. All right. In the first one, all right, propanal from propane. All right. So whenever you're doing these, it always helps to write down the structures of your starting material and your final product. All right. When you see the structures, a lot of times it's easier to visualize what could I do to get from one to the other. All right. So propanal. All right. This is the structure of propanal. The al part means it's an aldehyde. The prop part means there's 3 carbons in it. All right. So the first thing that comes to mind there is that you can either get it to it from the oxidation of an alcohol, or from the reduction, eventually from the reduction of a carboxylic acid. All right, so remember, an aldehyde, its oxidation state is somewhere in between. All right, the alcohol is the most reduced. If you oxidize it up one level, it's an aldehyde. You oxidize it up one more level, it's a carboxylic acid. All right, so that's a starting position. All right, going to what we're starting with, propane. And one thing about you, if you're asked to do any sort of synthetic reaction with propane, is to realize that really the only synthetic reaction we have with an alkane is radical halogenation. All right. So one thing would be you could take propane, all right, and you can convert it either into the alkyl chloride or the alkyl bromide. Both of those would be things that you could do through a radical halogenation. All right, and from what should stand out is we could get from this alkyl halide, all right, or as the IB likes to put it, a halogenoalkane, and convert that into this alcohol right here through an SN2 displacement reaction with this and hydroxide. All right, so how we could, going forward, all right, let's start with what we eventually figured out that we would need to start with. All right, we're going to start with propane, all right, and we could do a radical halogenation, and I just chose liquid bromine here. You could have also done this with chlorine gas, all right. The only difference would be instead of the alkyl bromide, you would end up getting the alkyl chloride. All right. So you want to give the reagent and the conditions. You would want to treat it with UV light. All right. So that's your light source there. All right. So once we have this chemical right here, we could treat that with sodium hydroxide. And the purpose of this reagent is you're going to have hydroxide, which is going to act as a nucleophile. All right. And this alkyl halide right here is going to act as your electrophile. All right, so if you wanted to draw the mechanism, an electron pair on the hydroxide, remember when this is dissolved in water, you're just going to have a hydroxide ion. The electron pair on that hydroxide would attack this carbon right here. You could draw these electrons going onto the bromine, and that would leave you with this alcohol as a product. All right, this alcohol could then be oxidized up to give the propanal. All right, so remember, going from an alcohol, oxidizing it up one step gives you the aldehyde. All right, so the next reaction right here, propanal. All right, so the same final product from propene. All right, so the thing that should stand out when you see propene is it's an alkene. All right, and the types of reactions that we've had practice with alkenes are the addition reactions. All right. So either a hydrogenation, where you turn the double bond, you essentially get rid of the double bond, turning it into a single bond. A hydration, which is where you treat it with acidic water, all right, and you add water across it. So when you add H2O to an alkene, you end up getting an alcohol. All right, there's the halogenation, where you treat it just with either Br2 or Cl2. And then there's the hydrohalogenation, where you treat it with either HBr or HCl. All right. So again, let's kind of work our way backwards here. All right. This is very similar to the problem before. All right. This aldehyde could be accessed by either of these oxidation states right here. And this alcohol right here, remember in the previous step we got to there by doing a radical halogenate. We had this intermediate right here. Well, the thing is that exact same chemical right there could be accessed from the this alkene. So remember, when in this step up here, we took the alkane and we got to it by doing a radical halogenation. All right, but the thing is that exact same chemical you could get to by doing a hydrohalogenation off of the alkene. So it's an addition reaction off this could give you the same product as a radical halogenation reaction from this alkane. All right, so how we would do that? All right, let's take our propene, which is the starting material, and we're going to treat it with HBr. All right, and one thing I want to point out about this is that this would actually be the minor product. All right, notice this is an unsymmetrical alkene, which means you have the potential to have either the Markovnikov or the non-Markovnikov product. All right, so remember the way it would work. You want to say mechanistically, all right, the electrons from this double bond are going to attack this hydrogen. The electrons are going to go on to the bromine, making bromide. All right, and so the question is, which carbon are you going to make the bond to the hydrogen? Would it be more likely to form the bond here, which would give you the positive carbocation charge right here, or would it be most likely to for the hydrogen to get attached to this carbon right here, giving you the carbocation on this carbon? All right. Well, it would be more likely. Remember, Markovnikov addition says it's more likely that you're going to have the carbocation form on the carbon that's got more carbons attached to it. All right, because that's the difference between having a secondary carbocation, if the positive charge were to form here, or a primary carbocation. All right, so therefore this is going to be the minor product. All right, and if you do the mechanism that to get this product right here, remember the original addition would involve a creation of a bond between this carbon here and this hydrogen. All right, so if we draw the arrow there, create that bond to the hydrogen there, that leaves the carbocation on this carbon, which that's a primary carbocation, and those are very unstable. All right, so this would be, even though you could make some of this, just keep in mind, it would be the minor product of that reaction. All right, and so once we get to this right here, essentially we're finishing it off the exact same way that we did right here. So same as above. Once we get here, treat it with sodium hydroxide to get the alcohol, and then we're going to oxidize the resulting alcohol up to the aldehyde. All right. So in the next step right here, I have to first of all I have to make a correction. This should be 3-bromopropene. All right. And this is fairly straightforward. Actually, we've already done this. All right, because this right here is 3-bromopropene, so it would be just this part of this synthetic route right here. All right, so you treat it with sodium hydroxide to get to the alcohol, and then you oxidize the alcohol up to the aldehyde. All right, so again, one thing that you're going to want to be very familiar with are the oxidation reduction steps. All right, and again, anytime it's an oxidation, it's acidified dichromate. Any reduction step, so for example, a reduction step would be going in the opposite direction here. All right, and then the reagents are either lithium aluminum hydride or sodium borohydride, and I encourage you to go back and review the videos on that. In the next step, phenethylamine from benzene. All right, so if you wanted, one thing that helps again is to draw your starting reagent and your end product. All right, so this is phenethylamine right here. This is benzene. All right, so this is something, we got to do something with benzene, and the only reaction that we have with benzene is the nitration reaction. So the conditions of the nitration reaction are a mixture of nitric acid and sulfuric acid, and you need to give this a little bit of heat. All right, but you end up getting nitrobenzene. All right, so nitrobenzene can be can be converted to phenethylamine through a two-step process. I would argue that it's actually just a one-step process. The first step is a reduction of the nitro group. All right, and so this is a reduction because you're losing oxygens off this. All right, you're also gaining hydrogens, so that's a reduction. All right, and the conditions for that are tin, metal, and hydrochloric acid. All right, and what that would give you originally is the ammonium salt. All right, of an amine. All right, so this is what you originally get, and this material right here is nothing but the conjugate acid of an amine. All right, it's the ammonium salt of this amine right here, and so all you have to do is to convert that essentially the conjugate acid form to the base form, and you could do that by treating it with some hydroxide. All right, and all that does is the hydroxide is going to, you could draw the bond going to one of the hydrogens, and that's going to end up freeing up this right here, which is if the term for that is you've made the free base. All right. One place that you might have heard that term before is drug addicts used to do what's called freebasing cocaine. All right, because cocaine in its normal state is in its ammonium form. All right, and sometimes drug addicts would convert it to its free amine form, which was a little bit more potent. All right, and that process was called freebasing. All right, because this is the free base. This right here is the conjugate acid of that free base. All right, so next to last problem, propylbutanoate, and I have to make this correction here. Instead of ethane, that should be butane. All right, and bromopropane. All right, so since there's a correction here, I would encourage you to, if you haven't done this already, stop the video, see if you can figure this out with that correction in mind, because with ethane, I can't see of a route that would give you that product. All right. Okay. So now that you've had a little bit of time to think about it, all right, let's start by drawing the eventual product and see how can we get there. All right. So propylbutanoate. All right. This is going to be propylbutanoate is going to be an ester. All right. So this is the propyl part, and the way the naming works, butanoate. All right. That means that it's an ester that comes from butanoic acid. All right. So whenever you have the O8, change that, take that 8 off and add an ic. All right. And whatever that acid is the acid that's used in making it. All right. So if you can kind of look at this part right here, imagine that this right here, that would be an oxygen hydrogen. That would be butanoic acid right there. All right. So the way that we can make this is through a Fischer esterification. All right. So this right here is butanoic acid. The alcohol that would be used would be this alcohol right here. All right. That would be just propanol, 1-propanol. All right. And that could be derived from bromopropane. And bromopropane could be is actually the starting material here. All right. So how do we get, actually, all right, so to get to the materials here, all right, so to get to the butanoic acid, we're going to start with the butane. All right, the only reaction we can do there is a radical halogenation. These would be the conditions that could give us the bromobutane. We could then treat it with sodium hydroxide. That's going to turn the bromide part into a hydroxide or to an alcohol. All right, and then we could oxidize that up. And here you're gonna, if you treat it with enough of this, you'll get it'll go, not just stop at the aldehyde, it'll go all the way to the carboxylic acid. All right, we could then treat that, so we have that carboxylic acid. We could make the required alcohol from bromopropane. We just displace this with the alcohol. So now we've got this chemical right here, and we can react them together to get this.